SwayamPrabha. Digital India. Educated India.
So time to get into multi-physics phase field modeling. We're going to start with an introduction, and then as you can see in here, tomorrow, so I'll stop whenever we finish. We have an hour more or less, and then tomorrow we will have discussion on corrosion and battery degradation. I think that's the plan for today. So today I'll tell you in general how to deal with any multi-physics problem, and I'll provide some examples of implementation and describe, particularly in Abacus, how you would implement some of these things. In places like COMSOL, it's straightforward, but the same way we do it in Abacus, you could actually do it in any other commercial finite element package. Or not commercial, anything that solves for thermomechanics, which is, I guess, all packages you can use. So just to provide a little bit of the motivation for why we're interested in these multi-physics problems, a lot of the work that we do in our group is related to tackling the energy crisis. And these are interesting problems because, there's a big push from the government, from society, to tackle those problems. But not only that, but we're also trying to, these are problems that are, I would say, of high scientific interest and challenge, because you have problems that are related to, as you will see, multiple disciplines. So this is tricky problems to solve. So you can see here, I don't know what the commitment of the government of India is, but in the UK, they're hoping to be almost, I think they want to be all the power system, all the power generation net zero in 2035, and the country has been completely net zero in 2050, and the EU has the same strategy to be completely net zero in 2050. And this is what I was saying yesterday, that hydrogen was so important, because the commitment is clear, and this now is a law in the UK. You have to be net zero, so you have to eliminate all sources of carbon emissions or compensate them somehow. So at the end of the day, you do need hydrogen here, because the ambition is quite strong. And these are very strong ambitions that politicians are putting in front of us. And engineers have done a remarkable effort, I would say, in tackling those, achieving those ambitions. I think engineers are, of course, driving the fight against climate change, against the energy transition, and they are really making remarkable progress, I would say. I think it's fair to say that it's impressive what engineers have done. And engineers have done miracles when it comes to, improving the competitiveness of renewable energy and other clean energy sources. Some examples here. So this is the price of a solar panel per watt in orange from the 70s into 10 years ago. You can see that the drop is really gigantic. It's amazing how much over a few decades this technology has changed. And in blue here, you see the increased capacity. You can see that we are, of course, in the second economy of scale as well. We're adding more and more solar panels all over the world. The same goes for wind energy. Here is the cost per kilowatt hour, again, since the 80s. And again, you can see gigantic drop. And then this is the global capacity. We're increasing and increasing the global capacity. And this is lithium-ion batteries. You can see here the energy density versus the theoretical limits that we can achieve, and how close we are getting. There's a gap in the data here, but how close we are really pushing batteries to their limits, to the thermodynamic and theoretical limits. So that's, I think, quite impressive. I think the problem is that, in a way, we kind of solve the easy problems. I guess, the easier problems is the ones that we normally solve first. But in order to achieve these very ambitious claims, these things need to keep going down. So you can see that they went down quite quickly, but now we are kind of saturating a little bit. You can see here in batteries we're reaching our limit. So we need to keep pushing these things down. And that's a challenge. That's complicated because we solve the easy problems first, but now we are left with the difficult problems. And so we need to, this cannot continue like this. If we want to achieve these things, this has to experience a big drop. So what can we do, as mechanical, civil, material engineers, what can we do to achieve this? One of the areas that we're working quite a lot is in wind energy. And as I said, it's amazing how the cost of wind energy has gone down. It's really a very competitive technology these days. But if we think of offshore wind energy, their life cycle management, it is still in its infancy. So they have a very short lifespan, the 25 years. They're designed to last 25 years or even less, depending on which country. If you think of a nuclear power plants are now there for 40, 50 years. And nuclear power plants are very challenging and have a lot of health and safety issues. So one can think, okay, why do we only, I mean, it's a new technology, so there's reasons behind this choice of 25 years. It didn't come out of the blue completely. But you know, I'm sure there's things we can do about it, right? With every new technology, there are things to improve. And I think we have improved a lot of them. That's why the price has gone down. But we can improve them even further in other areas. One is, you know, expanding the lifespan. And also the operation and maintenance costs are 80% of the investment costs. So because we don't know when these things are degraded, how cracks grow, we need to do a lot of inspections. Inspections are very expensive. So the life cycle management of these offshore wind turbines is very, very expensive because we don't know enough about it. And because it's a completely new technology, and we want to be on the safe side. So there's plenty of things to do. And if we can crack this problem, then we can for sure bring this thing down. And in fact, we work with Vattenfall. Vattenfall is a company who manages, it's a Swedish company. It's all over the world, but it's originally Swedish, and they're heavily invested in various energy sources, including nuclear, but also in offshore wind. I think it's one of the two key big players, together with Ørsted. It's a Danish company. And they manage and operate Hornsrev 1. This is what you see in the image. Hornsrev 1 is the oldest offshore wind farm in the world. And it's based in Denmark, and is the oldest, as I said, the oldest large-scale offshore wind farm in the world. And it was installed 24 years ago, if I remember well. So in 1 year, they need to make a decision on whether they extend the lifetime of this offshore wind turbine or they keep it as it is. And of course, as you can imagine, you know, if they manage to extend the lifetime of this offshore wind turbine by 10, 15 years, like the nuclear guys do with research, then that will have a gigantic impact on the entire wind energy sector. And of course, everyone is paying attention to this because this is, you know, the problem that we're thinking of. If this is the first decision, you know, this is a new technology. The Danes were the first to come up with these offshore wind farms. So in the UK, most of the offshore wind farms are 10, 15 years old at max. So we still have a problem that we'll have to fight in 10 years. But you know, this is the first example. So a lot of people are interested in knowing what they will do. If they decide to keep it, will things start falling down, and so on and so forth. So you may wonder at this point, okay, how do they determine where is this 25-year coming from? The 25-year comes from the fact that these are, you know, carbon steel metallic monopiles. And these metallic monopiles that are exposed to fatigue and corrosion. So fatigue because you get cyclic loading from the wind, from the sea currents, and from the sea waves. And then you get corrosion because you are in the middle of the sea. And particularly problematic is the area, what they call the splash zone, where the sea waves hit the monopile. That is the issue. So yeah, basically we want to understand this phenomenon, and we want to predict what should be the lifetime. Is this 25 years a suitable choice? How do they come up with this 25-year number? Well, they do it through real SN curves. So they do fatigue experiments. Remember we discussed on the first day, you take a cylindrical sample, you load it cyclically, and you measure the number of cycles to failure at different stress amplitudes or strain ranges. So they do this experiment, you know, they have a bar, they pull on their tension, eventually you rupture the sample, and then eventually you get a data point there. So for a given stress amplitude that they measure, they got a number of cycles to failure, exactly as we discussed on the first lecture. Then they change the stress amplitude, they lower a bit the load, failure happens a bit later, again, and you know, after a number of experiments, you get enough data points that you can do an SN curve, and you make sure your SN curve is, you know, conservative, is below the data points, but once you get the SN curve, that's all you need. And in the case of wind, then you look at your wind energy and you apply superposition, you assume linear elasticity, you apply superposition, and you say, okay, I have the waves, the loads from the waves, from the sea current, from the wind, the stress amplitude of each of them, I add them all together, and I end up with something that is, I don't know, 50 megapascals. So I go into this SN curve, I go to the SN curve, and I see the number of cycles to failure, and I get, I don't know, 10 to the 7, and then I know the frequency of my load, so I know basically how many years it will take to fail the component. So I say, okay, 125 years. So that's fine. But the problem is the corrosive environment. Corrosion is going to play a role in fatigue. And it's still unclear what role it plays. So there's a little discussion on whether corrosion maybe leads to pits, and that surface roughness is what diminishes the fatigue life. So this was the motivation of Sarah, the postdoc, the virtual fatigue experiments that I showed you, where we account for the effect of roughness on fatigue life. Some of the people said that it's a coupled effect between corrosion and fatigue. It's still very much unclear. But what the industry have decided to do is they apply a knockdown factor. So they bring down these curves by applying a randomly chosen, almost randomly chosen knockdown factor. It's based on some historic data that they have from oil and gas, which is very different conditions than what we expect to have for offshore wind. But anyway, they needed to do something, right? I mean, you know, engineers cannot be waiting for scientists to solve all the problems before they put the first monopile. They need to try things, and they go with the best guess, and that's very, very good of them. So they came up with this knockdown factor, which is a bit arbitrary, but you know, it's what they do. And then you enter again the graph with your stress range that you expect from your loading conditions. And then you can see, of course, you get a much lower number of cycles to failure, and then you get 25 years. So this is where the 25 years come from taking some data and applying a knockdown factor. So there's a lot of uncertainty here. One of the uncertainty comes from, okay, what knockdown factor do you pick? This is, again, chosen from some data that was not exactly under the same conditions, but also how even you generate data to build that knockdown factor. And this is quite complicated because, well, first, SN curves are not suitable when you deal with corrosion. Because when you deal with corrosion, SN curves has a number of I would say, assumptions embedded. The first one is that you apply superposition, right? We said we have loads coming from the sea current, from the sea waves, from the wind. So we add them all together into this number. Superposition you cannot really apply when you have corrosion. Corrosion is a history-dependent problem. So that's something you cannot do. This is also time independent. Where is the time here? There's no frequency, there's no time. Corrosion behavior is going to be frequency dependent. Corrosion behavior is going to be time dependent. So how you got these SN curves matters. You may be getting them in a conservative regime or in a non-conservative regime. So that's another problem. There's the various problems that are related to, of course, you deal with normally with welds, you have different materials heterogeneity, you have residual stresses, you have sharp stress concentrators. These SN curves, you know, they are dealing with smooth samples, and you know, you cannot just simply account for the stress concentrator factor because again, there's an interplay with corrosion. Corrosion is accelerated by mechanical fields, so you really need to solve the problem, and that's a complicated problem to solve because you know we don't really fully understand corrosion fatigue, and it's quite a complicated problem. And as you see, you are modeling things that fail over millions of cycles. So we'll get there. We'll discuss that probably tomorrow. But today I wanted to tell you, okay, as engineers, when we need to tackle these problems that come with energy transition, we need to be able to tackle problems that are multidisciplinary. It's not anymore mechanics, it's material science, it's chemistry, it's corrosion, there's multiple phenomena happening, and we need to resolve that phenomena. The good news, as I was saying in my seminar, is that computers are big enough that we can finally solve all those problems. We know what are the differential equations that describe each of those phenomena, and computers are big enough that we can solve all those coupled phenomena. We need to think about the couplings, but you know, this is what we have. So if we try to think of multiphysics problems, normally we have three equations, at least. We have one for the mechanical deformation. This is one that you guys know. So we normally solve for the displacement field. We will have a phase field as well, and then we'll have some other variable. That other variable we'll discuss later. Then you have the phase field equation. The phase field equation, you can see this looks a bit different than the one you've seen so far, because this is the general form of the phase field equation. So it's the same phase field equation that people use for microstructural evolution, that they use for corrosion, and for fracture. I'll show you in a minute why the same model that everyone uses in different disciplines actually can be represented by one. And then you have an additional field, and that depends on what problem you're interested in. It will be heat transfer if you're looking into thermomechanical cracking or thermomechanical fatigue or whatever. It could be hydrogen if you're looking into hydrogen. It will be hydrogen transport. So this chi variable could be hydrogen concentration, it could be temperature, it could be fluid flow, maybe pressure if you're looking at hydraulic fracture. It could be any quantity that you may be interested in, basically. But this is the general form. Whatever problem you have, whatever coupled physical problem you have at least your mechanical problem, your phase field, and then some extra field. It could be temperature, it could be hydrogen concentration, it could be lithium ion concentration, whatever you decide. So let me first start by saying a few things about the phase field. As I said, this phase field equation looks very different from the one you've seen before. This is the one that the macrostructural solidification phase field community uses, but I'll show you in a minute how you can get from there to the fracture one. So the way the macrostructural solidification community builds phase field is by putting a thermodynamics picture, and they say in every problem we have a bulk free energy and an interfacial free energy. So there's a cost associated with interfaces. The bulk free energy might depend on some internal variable beta and the phase field, and then the interface between those two phases will depend on the gradient of the phase field. And then what they do is they do some sort of interpolation. So they say I have a phase 1 and a phase 2. I have an interpolation function. That's something we call G in fracture. So in fracture, if you think of phase 1 and phase 2, will be crack material points and crack material points. But in microstructural evolution, it will be material 1, material 2. So you have a bulk property 1, bulk property 2, and then you interpolate with this function, such as remember the blue and the red phases, the example that I showed you with the phase field. When the phase field is equal to 0, you need to make sure that this is dominant and this is 0. When the phase field is equal to 1, this goes away, this becomes 1. That's the idea. So you interpolate between two phases, and then you have some double well potential, and then you have this energy term where you have some kind of interface energy related, a penalty to that energy. You penalize in interfaces. This is the general form. And then in order to go from this free energy functional to an equation that you solve in finite elements, your balanced form or the strong form of your equation, then what you do is you apply this relaxation condition. This is what they call the Allen-Cahn equation. The microstructural evolution community calls the Allen-Cahn equation. So you take the stationary of the functional, you equate it to this, and you end up with something that looks like this. And this is the way they build all the phase field models that are not fracture. Fracture came independently in a different way. But I'll show you how it's the same. For example, if I talk about corrosion, and I will discuss that tomorrow, corrosion phase field models are very similar to microstructural phase field models. So the idea is that your bulk energy is the chemical free energy density. You could also have some strain energy density, but that we'll discuss tomorrow. The simplest corrosion problem that you can think of, where you neglect mechanics, you have a chemical free energy density. The phase 1 is the solid phase, the metal, and phase 2 is the liquid phase, the electrolyte. So the seawater, for example, if you have a metal corroding in the middle of the sea. In fracture, the bulk energy is the strain energy density. In phase 1, that is the uncracked material, that corresponds to the strain energy density. And in phase 2, it corresponds with the crack. It's 0. In the crack, we carry no load, so the bulk energy, the strain energy density in the crack is 0. So this is the idea. So it's the same approach. We interpolate between two quantities, but in fracture, the two phases are the crack phase, where they have no strain energy density, and the uncracked phase, where you have the strain energy density. That's the idea. And when you do that, let me focus on the fracture case. When you focus on the fracture case, the other thing that you need to consider is that we deal with a static problem. So normally in fracture, as I told you the other day, you could have this term if you want to get some extra convergence properties. But if you don't care about convergence, normally most people will just say this guy is 0, fracture is a static process. I mean, it can be a rate-dependent process if you have other rate-dependent phenomena. For example, you can have material rate dependency. If you have an impact, a dynamic, your fracture will be different, but it will be different because the constitutive behavior of the material is rate-dependent, not because the fracture process itself is rate-dependent, or any other rate-dependent phenomena like hydrogen. It will be rate-dependent because it will take time for the hydrogen to go there. But the fracture process doesn't know anything about it. It just knows how much hydrogen comes as a function of time. So we normally take this guy to be equal to 0, and then when you equate, you make this equal to 0, you end up with this expression. You make also F2 equal to 0, you kill it here. And then you can see that if I look at the phase field fracture equation that I've been discussing the entire week, I can make this, I can define this W as GC divided by 2L, this kappa as GC multiplied by L, and I get an expression that is identical to the one that, So basically the idea is that you can come up with a generalized formulation that you can particularize to macrostructural solidification, whatever you're interested in, but also fracture. So even though they were originated in a different way, they can be condensed in one formulation. And then if I think of the 82 model, the conventional phase field fracture, so I have this degradation function, and here it can be a bit confusing. Normally we call it G, but the macrostructural solidification community calls it H. It's some sort of interpolation function. We call it degradation function. This is the usual form. And then you have a dissipation function that we don't call G, but they like to call G, so it's a bit confusing. But anyway, when you do that, you substitute, and this is the equation that you've been seeing all these days, basically. And so you don't think to understand any of this, but I just want to say, whenever you see people talking about phase field, or you deal with a code that handles phase field, the idea is that you have no problem in dealing with that. You can particularize it to phase field fracture in a straightforward way. You just need to think of being a static problem, so you make this guy equal to 0, considering that your strain energy from the bulk, the energy from the bulk that you care about is the strain energy density, and then considering that your two phases are cracked material and cracked material, and then making these analogies. Okay, so now let's look at the additional field. I'm trying to be as general as possible. So this is the general equation for any additional field. This could be a temperature, could be a pressure, it could be anything you are interested in. So this additional field, as you see, has multiple quantities. So there's the quantity that I'm interested in, this chi parameter, its gradient, and it can be coupled. It could be influenced by the stresses, by the displacements, and by the phase field. And you can see that the key point, the key takeaway of today of this lecture is that we can accommodate this additional field using the analogy with the heat transfer equation. So this is the general heat transfer equation, and this is available in all commercial finite element or non-commercial finite element packages. Everyone can do thermoelasticity. So you have some sort of internal heat generation, a density, some sort of vector here with the gradient, and R. So you can pick any of these quantities, it's the same thing. So for example, if you're dealing with thermomechanical fracture, let me particularize your examples. If you're dealing with thermomechanical sample, well, that's straightforward. Normally it's the same thing, so it's the same analogy. So normally the heat transfer equation looks something like this. So you can define this as U, then you can define this as K, and then you can define this as R. But basically the idea is that you can use in Abacus what is called a UMAT-HT, and I'll show you in a minute. But the idea is that you can accommodate with a general form of heat transfer equation any other phenomena. So the easiest one is thermomechanical fracture. You will solve mechanical problem, phase field problem, and this additional field will be temperature, and you can see how you accommodate each of the phenomena. If you're dealing with hydraulic fracture, remember we need to solve a mechanical deformation problem with an effective stress per mechanics, phase field fracture problem, and then your additional field will be you're solving for pressure, you use Darcy's law. So this is the equation that we solve in thermomechanical in hydraulic fracture, Darcy's law. You can see that if I look at the shape at the heat transfer analogy, it looks the same, right? This could be my density. All of this can be U. All of this can be F. You have a divergence of a quantity here. All of this can be F. And in this case, Q, this flux that we're imposing could be R. So the heat transfer equation, not only you can make an analogy with phase field fracture, but you can make an analogy with almost every other multi-field equation that you're interested in. The other example is hydrogen embitterment. Remember, how do we solve hydrogen transport? Is this equation here. You have the hydrogen concentration here, the rate with respect to time, and then you have this divergence term when you have this diffusivity, concentration, temperature, hydrostatic stress. So again, this could be equal to 1. How do I make an analogy? You can see the analogy. R becomes 0 in this case. F becomes this chunk over here. Rho becomes equal to 1. And most commercial finite element packages, including Abacus, will give you an opportunity to define this guy, to define this guy, and to define this guy. In the case of Abacus, in a UMAT-HT. So you can define all these things. And then in the case of a general phase field model, the same thing. So this is valid for microstructural evolution as well. If you wanted to implement macrostructural evolution and mechanical load into Abacus, very simple. With a UMAT-HT, you define this guy as 1, R equals 0. This becomes your F. This becomes your U dot. And so you need to, put a line of code in your. I'll show you in a minute how you do it. And this is useful for phase field corrosion. I haven't discussed yet phase field corrosion, but the way that the phase field corrosion equation looks like, basically in phase field corrosion, in the simplest problem you can have, you need to solve for two things. You need to solve for the corrosion process, which is the phase field. The phase field tells you how the corrosion front evolves. And you need to solve for the concentration of metal ions. So as part of the corrosion process, you are kind of detaching metal atoms from the metal into the electrolyte. So you need to model how those metal ions move through the electrolyte. So this is this transport equation here. So you can see that the same equation can be used to both of them, right? So here this is U, this is F, this is U for the concentration, and this is F right there. So you can always find an analogy. So you just need to tell Abacus, I'm going to solve a thermomechanical problem, and now you define these things inside of the UMAT. That's the idea.
Is this a multi-phase field? What material science community also has?
You could do multi-phase field. So for example, when we do with corrosion, if you only deal with material dissolution, we only have one phase field, and then we have a concentration. So one will be the phase field will be the non-conserved quantity, and the concentration will be the conserved quantity. But for example, when we look at a stress corrosion cracking, where we have both material dissolution and fractures, material rupture, then we have two phase fields, the fracture one and the corrosion one. Both can be built in this phase field analogy, and as I will explain in a minute, we can solve as many of these additional equations as we want in Abacus with a trick that we have now. So this could be done for multiple phase fields as well. Yeah, and phase shield fracture. This is something we discussed the other day. So again, we were using a slightly different version of the heat transfer equation, but you can see that we can define the phase shield fracture as well. So now the question that you may have is, okay, Emilio, that's all fine. You know, if I look at hydrogen embitterment, for example, that you have heard about it much more. That's all fine. You told us, Emilio, that you do thermomechanical, you do this thermal analogy, so you have Abacus solves for temperature and displacement. So you replace, you cheat Abacus and tell them that the temperature is going to be your phase field, and in that way we solve a fracture process. That we explained the other day, right? Now you may wonder, okay, how do you solve for temperature for the phase field and temperature for the hydrogen concentration? Because, okay, you say, Emilio, I understand. I can see that one could use the heat transfer analogy, so I can tell Abacus temperature is actually concentration of hydrogen, or temperature is actually a phase field. But how do I tell them both? You know, Abacus only has one temperature. So the way you do that is by what we call a twin-part process. So this paper is under review now, but I'm happy to send it over and send the codes if any of you are interested. The idea is that, so it is true, Abacus can only solve one temperature at a time. Abacus never, I guess the Abacus developers never thought that they will have multiple temperature fields interacting. That's not physical. But you can do, the way Abacus numbers elements, you can have what we call conjugate elements. So you could have basically, you do your standard Abacus problem, you define your part, you measure your part, and then you duplicate your part. And the moment you duplicate your part, Abacus numbers elements in such a way that there's a unique relationship between them. So if this is my part 1 and this is my part 2, this element 1 is going to be connected to, the numbering is such that, you know, there's a local element number and a global element number. Abacus is going to use the same local element number, so this is 1, 2, 3, 4. Assume you have a very simple model with 4 elements. You're going to have element 1, element 2, element 3, element 4. Abacus is then going to call element 1 locally, 2 locally, 3 locally, 4 locally, or 5 global, 6 global, 7 global, 8 global. So you know basically for one part, what is the element that corresponds to the other part. And then you have a four-term module in your subroutine that passes things around. So basically you have, for example, one typical way that we solve this thing is that you have a UMAT subroutine. So you have two parts. In the UMAT subroutine, in the same UMAT, you can always say, you know, part 1 is going to have a material that is going to be called material 1. Part 2 is going to have a material, the same material everywhere. It's going to be called material 2. And then inside of the UMAT, I'm going to say, are you calling something that is material? Are you part of element global element 1? Yes. Okay. Then we're going to solve for material 1. Are you part of element 5? Then we're going to solve for material 2. And in material 1, for example, you could choose the first part to solve for displacement and phase field, for example. So you could solve for stresses and concentration. In material 1, you define your mechanical problem, so that would be stress and material Jacobian. And then in the UMAT HT, with the analogy that I showed you before, you will solve, for example, for, let's say, phase field fracture. You will solve the problem for phase field fracture. And then in the part 2, when you call part 2, you will say, okay, you're calling part 2. This is an element that belongs to part 2. The UMAT, I'm going to put it all 0 because you already solved your mechanical problem. In the UMAT HT, I'm going to solve for this temperature that corresponds to hydrogen embitterment. So I'm going to define these terms. You need to define basically, you need to define this guy, and this guy, and the derivative with respect to temperature. In the UMAT HT, you define those terms corresponding to hydrogen embitterment. So Abacus is solving one temperature in one part and a second temperature in the second part, and you can send them both apart because, of course, the problem is fully coupled. I need to know how much hydrogen I have, so I need to communicate between material 2 and material 1, but you can do that in a four-term module because you know the relationship between the elements. You know that element 1 is going to be element number 5. So I said, okay, temperature in element 5, I'm going to call this hydrogen concentration, and I'm going to pass it over, and now I can reduce my toughness in element 1. That's the idea. And I'm not going to get too much into the details, but the quantities that you need to describe in Abacus are this internal strain energy, the derivative with respect to time, the derivative of u with respect to t, this f, and then this delta f with respect to temperature, and delta f with respect to the gradient of temperature. So this is the quantities that Abacus does. For each of those, I mean, you can derive it yourself. It's straightforward, but we also have it in the paper. So you can see, for example, I don't know, the easiest one maybe is hydrogen transport. So this is the case. This is equal to 1. This is 0. This is the big F. Remember, you had a big F. So this is the df with respect to dt, and this is the derivative, the second derivative with respect to the gradient of temperature. So this is the idea. So I'm going to show you one example with facial fracture, hydraulic fracture. I think this is a good simple case. So I'm going to implement, using this analogy, the fracture equation and also the fluid flow equation. So these are the terms that I need to define. There's no second derivative of this guy with respect to, or derivative of this guy with respect to the gradient of temperature, but there is with the, so I need to define this thing, I need to define this thing, and I need to define this thing. So the two equations I'm implementing is the fluid flow and the facial fracture. That's the idea. So let me show you the code so you can relate it to the other thing. Very simple code. So now we have a Fortran module. This allows us to communicate between subroutines. So we have something called K-transfer, and we say, okay, we have various quantities that we want to transfer. So, for example, if you think of the hydrogen enrichment, you may want to transfer your hydrogen concentration just to know how much you need to degrade your toughness. You want to transfer to the hydrogen concentration your gradient of hydrostatic stress or your hydrostatic stress to see, how much it affects diffusion. So every problem will have different quantities to transfer, but you transfer through this kind of K-transfer, basically. This is the idea. Then you have a UMAT. In the UMAT here, you see this is the extra line. You got two extra lines. One is this get part info, so this tells you which element you are, which part you are, and so on. But you have this extra line that says, if CM name, this is basically a variable that Abacus sends to you that tells you which material you are, equals material 1, then please proceed as usual. And here you see the same as before, right? So this is, you define your Jacobian matrix, you define Young's modulus, you define Poisson's ratio, you define the phase field length scale, the toughness. This is what we saw before. We have here an extra solution flag that tells you if you want to do monolithic or staggered, and you can do all of the combinations. So by the way, you see more details in the paper, but you can do almost all combinations. You cannot solve everything monolithically. That's the only thing you cannot do. But you can do these two monolithically, this one single pass staggered. You can do, so here you see we are solving in part 1 the U and the phase field. In part 2 we are solving this G parameter, the extra variable that you care about. So you can solve these two monolithically, these two staggered, single pass, multi-pass, whatever you want. There's many options there. So you have this solution flag that tells you, whether it's monolithic or staggered, you pick. Then in this case, because it's hydraulic fracture, we give an extra property that is Biot coefficients, some domain indicators. Then we quantify the phi, because in this case we are in element 1, part 1. So the phi means the temperature is actually the phase field. This is the same as before. We are recording the latest value of the strain energy density as a state variable. This is to enforce the reversibility, the history field. And here, this is the degradation function. By the way, you see that here we have this extra 1 to the minus 7. I told you that this kappa value or k value, you can increase it if you want to get better convergence, if you want to go to the minus 5 or something along those lines. That is the first 50 lines. The next 50 lines are a bit different. So it's similar to before. You build your elastic stiffness matrix, identical to before. I'm using Lamé parameters, Young's modulus, Poisson ratio. Using the usual expressions, you build here your stiffness matrix. Exactly the same as before, as we discussed the other day. You update your strains. So you have a strain is strain plus increment in strain. Abacus is giving you the increment strain. This is all integration point quantities. You calculate your stresses. It's multiplication of the material stiffness matrix with the strains. So this is, I'm just doing to clarify. This is increment T plus delta T. And what I'm doing here is calculating based on, in tensor notation, that will be the calculation of the stiffness matrix. So it's identical to what you see before. So the only change that you have seen before now, relative to the code that you saw before, that was super easy, is, there's additional details that are removed from the previous code just to make it a bit simpler, but one is this kappa value that you can have in the previous code as well. The fact that I'm storing a state variable, this is the phase field, they say the strain energy density to enforce the reversibility. That could have been part of the previous code. I remove it just not to make it as simple as possible for you to visualize. The same goes for the flag variable. The previous code, if you download it from the website, you will see that it has also monolithic or staggered. And then, of course, I have extra parameters here because I have a multi-physics problem. So I have Biot's coefficient and these domain indicators. And then I have these two extra lines. I'm doing something different if I have material 1 than if I have material 2. So I'm doing this extra line. Otherwise, everything is the same. I compute the strain density, all identical to the same. Here, I define my history field. You can see it's the maximum of my strain density and my old value of the strain density that I'm storing in this state variable. This is the idea. So this line was not before, but it could have been. It's not related to multiphysics. It's just the history field. Then I degrade my stiffness. That's fine. And then I stored in some state variables quantities that I care about. That's, you know. Now we come with parts that are related to the hydraulic fracture problem. So in the reservoir domain, I define some auxiliary fields. I define in the transient domain how these auxiliary fields change as well. I store those auxiliary fields here in this quantity that, as you can see, belongs to the Fortran module, because I want to transfer those quantities to so these quantities depend on the phase field. Remember, when you do hydraulic fracture, you have three domains. You have the crack, the reservoir, and in between, and you need to interpolate between the phase field to decide how properties vary. Since I'm solving the fluid flow problem in the other part, I need to store what is the value of those auxiliary fields to transport it to there. So if I were dealing with a hydrogen transport problem, maybe here I will have my hydrostatic stress and will store it here to use it later. And then you modify those quantities, the Biot coefficients. Then you degrade the stresses, similar to before. Then this is effective stress quantities because it's hydraulic fracture. And then that's all. And then you see the difference here. If the material, now we have an else if. So if I'm in part 2, because I'm solving, remember, I decided to choose, you can change if you want, but I decided to solve the mechanical problem in part 1, the fracture problem in part 1, and then the fluid flow problem in part 2. So therefore, I say, okay, if I'm in material 2, then assign this value equal to 0 and go away, because there's nothing I need to do. So that's the only difference. So you have extra things due to the fact that you're solving for an extra problem. But basically you have this categorization. If in your UMAT is material 1 is part 1, whatever problem you're solving there, material 2 is part 2. And then you have this UMAT HT subroutine. You can see it here. This is what the Abacus call a user material for heat transfer. That's UMAT plus HT. These are the quantities that Abacus sends over, so temperature, some derivative, coordinates, and so on. And again, what am I doing in the UMAT HT? Here I'm solving for the phase field fracture, and I'm solving for the heat transfer problem. So if these are the ones that I'm solving for. These two I'm solving in the UMAT HT. So I need to, Abacus tells me, oh, okay, in the UMAT HT you tell me what is U, what is du dt, what is du dg, what is flux, what is these variables, which are basically corresponding to these quantities. So I need to define those quantities. I happily do so. So if my material is 1, I know I'm in part 1. The quantity that I care about is the phase field fracture. So I need to define these quantities. I mean, the codes are there. You can download them and use them without understanding what goes inside of them. But if you happen to have a couple of physical problems that you want to simulate in a UMAT, this will be the procedure to follow. So very simple. You just check in your differential equation. You look at the heat transfer equation. You look at your equation. You group terms. You say, okay, this is the R, this is the F, this is the U. Then you take the derivatives. And now basically in Abacus, you just come this little code where you say, okay, this is going to be the temperature. I'm going to take the state variables. Now U is going to be this expression here, U plus blah, blah, blah. Remember, it's this. You see here, U plus blah, 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 blah. Du dt is this. Du dt is this. Du df is 0. You can see it here. The flux is also 0. And then the final piece of code, this is where we are here. This is the final piece of code. And then that's for the phase field fracture equation. It was pretty straightforward. And then you have the other material, which is basically the Darcy's law, basically, right? So you need to solve the fluid flow equation. And here, again, you have the terms there. So relatively straightforward. This is the whole code, by the way. So in material 2, you say, okay, I mean, it's not such a small code as before. It's not as clean. But you can imagine that if you have to solve this with your own finite elements, this will be a very long code because you have to discretize each of those variables. So here you're solving everything in strong form. So again, you take the properties, so fluid density, reservoir porosity, fluid compressibility, all the relevant quantities, you update the pressure, you transfer the inputs, the quantities that you took from that, the quantities that you took from those Fortran modules, you bring it over, and then you basically interpolate, modify with the phase field variable, and then you define these quantities that Abaqus is asking you to define. They ask you to define U, du dt, du dg, du df, df dt, and df dg. And you've gone through the processes and you've seen how it's done. So again, it's a bit dense now. It's maybe easier to follow for those of you working with Abaqus, but I'll do a quick summary just for you to understand what I mean.
So this monolithic and staggered scheme already inbuilt in Abaqus?
Yeah. So every time you solve a thermomechanical problem, Abaqus gives you the option of solving for displacements and temperature at the same time, or segregated, one and then the other one. Yeah. So then you can tell Abaqus what to pick, and then you can, because you have two parts, you cannot solve all three field quantities at the same time, but you can solve two monolithically, one staggered, and the multipass. There's multiple options.
We are not using any L flag to tell whether to use monolithic or staggered.
You are used. So for example here, there's various ways you can do it. So you click a value. So there's two ways. You can click at, so you can pick the solver into Abaqus, but you can also do it yourself in the sense that, for example, if I take if you think of the phase field and fracture problem, right? So my displacement problem has a phase field. Well, I don't need to write it. My displacement problem has a phase field, and my phase field fracture problem has a strain energy density. So you could store your phase field from the previous increment. Abaqus will call both at the same time. But instead of taking the phase field from the current increment, you could take from the previous one. You store it. Or the same for the strain energy density, you could use the previous one and store from the previous one. So let me just summarize. It's a bit dense for those of you not familiar with Abaqus. But I just wanted to know, if one day you need this, what will be the protocol? So you guys will be dealing with a problem that has mechanical deformation, I imagine, most of the time. Then you have some sort of phase field. It could be corrosion, it could be a fracture, it could be anything. And then you may have an additional field. For some of you, this will be hydrogen concentration. Some of you will be lithium concentration for a battery. For some of you, it will be hydraulic fracture, there will be fluid flow, whatever you want. Thermomechanical fracture. The only thing you need to do is for whatever problem you have, maybe I'll bring the hydrogen one, it's the easiest one. For whatever problem you have, you know what is the differential equation of your problem, the strong form. You look at it, you look at the heat transfer, and you say, okay, how are they similar? So here I can see there's nothing like R. I have terms that depend on time. This derivative means derivative with respect to time. I have a term that depends on time. I have a term that is inside of a gradient, of a divergence, and then nothing else. So R is 0. I have a term that depends on a gradient. Okay, what depends on a gradient? All of these guys. So this guy must be F. And then I have a term that depends on the derivative with respect to time. This must be U. That's the only thing you need to do. You look at your equation, you look at this. Then Abaqus will tell you, okay, that's great. So you tell Abaqus, solve me a thermomechanical problem. Because you have now 3 fields as opposed to 2, and Abaqus can only solve for 2, temperature and displacement. You need to cheat Abaqus by creating a duplicate part. So the process is the same. You create your element, your model, you mesh it, and then at the end of the only extra step you need to do, you duplicate your part and define a material for that part that is going to be called material 2. So part 1 will have material 1, part 2 will have material 2. And then in the code, you have some quantities that you're going to move around, and that's straightforward because Abaqus calls elements in a consistent way. So the moment you duplicated your part, Abaqus called all the elements in a consistent way. So if you have 4 elements, it's going to start with 5, and it's going to follow the same ordering. So you know basically which element corresponds to which. So the storage and transport of things are straightforward. Abaqus requires you to define in these variables, in a UMAT, this quantity. So it's U plus this, plus this, plus this, plus this. So you go back to your equation, you write those things down, and then the only code that you need to do is the same code as you had before, but you do have a Fortran module to transport whatever you need to transport. For example, in the case of hydrogen, you want to know hydrogen in the fracture problem to degrade your toughness, and you want to know hydrostatic stresses in the hydrogen problem to drive hydrogen diffusion. You have an if that calls material 1, and you define the usual code, and then you have an if for material 2, which is, in the case of the UMAT, it's just zeros because you're not solving a mechanical problem. In the case of a UMAT ST, if material 1, it could be phase field fracture. If material 2, in this case, is fluid flow. So you just assign your different variables, and that's all. And you call this routine. So that's all. It looks a bit all a bunch of lines of code that you haven't seen before. But what I'm saying is that it's not too complicated. It's only this process. And you're solving a very complicated multiphysics problem. So just to end with some examples. So this is, for example, thermomechanical fracture. So this is the classic benchmark that I showed you before. They immerse something in a bath that is at room temperature, something that is heated up. And this thermal shock causes cracks to develop. So very easy, very quickly to do in Abacus just with this kind of codes. Hydraulic fracture, I discussed yesterday. Everything that I showed you yesterday of hydraulic fracture was computed using this analogy. So everything is in Abacus at the integration point level. You don't need to code. You don't have to do anything. All those codes will be made available, but all those things you can capture. Hydrogen embitterment, we also validated with other implementations. Before we were doing everything in a user element. Now we do it all in the UMAT. The hydrogen embitterment code, by the way, has a slightly extra part, which is the computation of the hydrostatic stress gradient, but we'll discuss later. And corrosion, which is what I'll be discussed tomorrow. We can also implement phase field corrosion, and we have validated that with. So this is a paper that is currently in the review, but this is the idea. So any problem that you have, thermomechanical fracture, corrosion, and from a scientific point of view, those of you interested in, of course, publishing new papers and so on, a lot of interesting problems lie at this interface of these problems. So for example, we did phase field corrosion, we did phase field fracture. We have combined them once, but we never combined with fatigue, for example. You may have never combined thermomechanical. I've seen people doing thermomechanical fracture, but I'm not sure if anyone has done phase field fatigue and thermomechanical loading. And thermomechanical fatigue is a big deal. So it's, in a way, this very simple implementation allows you very quickly to fill those gaps that are important, not only in order to get a paper out, but in order to solve an interesting scientific problem. And if you talk to industry, for example, thermomechanical fatigue is a problem all over the place. So having a tool that can do thermomechanical fatigue is not something you can do in commercial packages, and it's something that you can do with these tools pretty quickly at the integration point level. So maybe you have even fretting fatigue, you have contact, all those things outlet into Abacus, you can do it quite straightforward. So I think it's a quite powerful technique. And again, you are solving for at least 4 degrees of freedom per node if you have a 2D problem, so two displacement components, 1 phase field and 1 extra term. But 4 degrees of freedom per node is not that heavy these days, so I think that's doable. Okay, we have 5 more minutes, so maybe time for questions, and then we can wrap it up.
What if we have another field solution in addition to the additional field solution? Then do we have to incorporate material too?
Yeah, so you could expand this as many times as you wish. So you could have, if you had multiple phase fields, or you have temperature, hydrogen, and you could add multiple parts, as many as you wish. So we're doing now with crystal plasticity, thermomechanical, hydrogen diffusion, and we have multiple physics.
And one more question, what if time constraint is the limit? Which would be preferable, like monolithic for mechanical and phase field, followed by staggered, or all staggered?
So the only disadvantage with this one is that you cannot do all full monolithic, because the way Abacus calls one part and then the other. That being said, it's not a big deal, because you rarely want to do all full monolithic. Is computationally not convergence much worse. And the same step is defined for all cases, so you cannot uncouple step jumps. You cannot just say, oh, this one is going to be it's going to take much bigger steps than the other ones. You will still need to have a fully consistent backward Euler method anyway to do those things. So I think you are limited in that case for the problem that you need to solve in the smaller steps, whatever it is. So if the fracture requires small steps, you're going to have to solve the hydrogen transport in small steps, which is kind of what will happen in reality. You need to resolve what is happening in terms of what the phase field hydrogen is doing as the crack grows and things like this. Yeah.
So here we have created the 2 layers, 2 duplicate layers.
Yeah.
When we will visualize the results in Abacus, then we will have 2 layers that will be shown. So we want to pick any element, so which result it will show.
Yes, a good point. So you are solving for 2 parts. Abacus is solving for 2 parts. So when you visualize, for example, the results, you will plot some results in one part, the other results in the other part. Both parts will look identical. A good question is what happens when you have large strains, because then they have finite deformations and so on. This is all so far small strains. Maybe you need to solve the mechanical problem twice just to make sure that you get the right deformed shape and so on. But assuming small strains, you are safe. And then you'll have 2 parts. In one part, when you plot the temperature in one part, they're identical. But Abacus will show 2 parts next to each other. When you solve the one in one part, the temperature in one part, you will see whatever variable you're solving there. It could be phase field fracture, and in the other part, it will be the hydrogen concentration. I don't know if that answers your question more or less.
Actually, we will pick any element, like we want to visualize the result. We will pick any element. So it can be either from layer 1 or layer 2. We don't know.
Yeah, so when you assign to the element in Abacus, when you send the material, when you say part 1 has material 1 and part 2 has material 2, Abacus know that each element belongs to different parts. So that's not a problem. The only thing is that you need to, of course, communicate between them, because you want to pass the hydrogen concentration from one part to the other, and you want to pass for that particular integration point, so you need to find the equivalent integration point. But because the way Abacus numbers a part that you just duplicated, you are safe on that front. You can use the subroutine easily.
How are these two parts linked or assembled? That's a little bit easy.
What do you mean, how they are cell assembled? So,
You have two parts, right? You should tell Abacus that they have contact or you have to assemble them together. So typically we put the two parts next to each other.
yeah, so these are floating apart. They are not in contact with each other, because you are solving, if I think, for example, of thermomechanical fracture, I would solve in one part, I'm applying a displacement, and I'm seeing how my phase field evolves. In the other part, I'm seeing how my temperature evolves, and my conductivity will be depending on the phase field. So I just have them floating apart, basically.
Same boundary conditions for part 1 and part 2.
In part 1, I will have the boundary conditions related to, again, assuming a small strain, so it's a small displacement formulation, so the geometry will not change. In part 1, I will apply the boundary conditions for displacement and fracture, whatever, if I have. And in the part 2 will be the temperature boundary conditions. So you're solving the heat transfer problem in one part, and you're passing around just the variables that you're interested in. Yeah. That's the idea.
Just a follow-up on this one question. Then you get two phase field from the two different parts, right?
You could. So in the examples that I discussed so far, I didn't discuss that one, because I thought it was easier to illustrate it with temperature or hydrogen. But for example, when we do a stress corrosion cracking, we solve for, so the question is, do you want two phase fields? If you have simply a multi-physics fracture problem, you don't need the second. What do you need?
If I have both mechanical and the corrosion.
Yes. So the case where we have done that one is precisely that. So in that case, we solve mechanical problem and phase field fracture problem in one side, in one part, phase field corrosion problem in part 2, and a concentration problem in part 3. So in that case, we solve 3 parts. You can solve as many as you wish, basically.
How do I get a coupled solution?
So in the case of the depends on what your couplings are. In the case of the phase field corrosion and fracture, this is up to discussion. Depends on, different people may have different answers to that. But let me just, what did I do here? So you need to think of how they interact, and that's, I would say a big topic of discussion. It was a JMPS paper published a couple of years ago. We came up with the best way we thought. I think in this case what we did was, you had a degradation function for the phase field fracture, I'm going to call it, and then a degradation function for the phase field corrosion. I'm going to call it D of dissolution, multiplying, your balance of linear momentum. So what happens here is that, whether you multiply them, what you do with those is up to discussion. I think you need clever experiments to figure out how they are coupled. But they must be coupled in one way or another. So what you do is, in part 1, so I'm solving this problem, the mechanical problem, in part 1. So I have this Fortran module that communicates between the subroutines. So in that Fortran module, I stored in this element 7, the phase field corrosion for this integration point 1, just to take an example, phase field corrosion value in that integration point 1, element 7. So then when I'm dealing with my mechanical problem, which I am doing in element 3, integration point 1, that is the equivalent, then I say, okay, please take from that Fortran module where you store your phase field dissolution, take that value and plug it in here. So that's the idea. All the variables that you need across, you store them in that Fortran module, and that Fortran module communicates against subroutines. There's only one issue with this Fortran module, is that if you are doing high performance computing across multiple nodes, multiple cores is okay, but across multiple nodes you need to add some stuff to make sure that the information is not lost. I think that's the only thing one has to be careful with. But in principle, you have this Fortran module, it's like in MATLAB, like a global variable. So You save it there, and then you can pass it over. So depending on the problem, you may need to pass over some things, some other things. That depends, but you can pass over all the things. And because of this element numbering of Abacus, it's straightforward to know which is your point in that part that corresponds to that point. So in a way, it's like if you were solving a model in Abacus for, let's say, couple deformation fracture, and every time you did an iteration, you call another separate model in Abacus and solve a temperature, for example, one, and then call back again, and so on, more or less.
Something like superposition.
Kind of. There's no superposition itself, but it's like you are dividing things into, yeah.
So for solving heat transfer, rather than solving displacement and phase field together, we can do like displacement and temperature together, and
Yeah.
phase field separately, because
You
already
pick.
met HT is there.
You pick. The only thing is that you cannot solve, you can solve these two fields monolithically. So fields within the same part you can solve monolithically. Fields in different parts you need to solve staggered. It can be multipass, but it has to be staggered. So normally you pick here the fields that you want to solve monolithically, and then you pick here any other field. So you could do thermomechanical loading in part 1 and phase field fracture in part 2. Yeah. Yeah. Exactly. Okay, if that's all, thank you all very much, and we'll see you tomorrow for the last day. Thank you.